to Hawaii. And I never swim any other time of the year at all for any reason. If you call and ask if I've swum, I say yes, that actually is evidence that it's winter. EP is less than 0.05 of that observation, but that observation is evidence that it's winter. So this is the core problem. And I believe, it's certainly a problem for the journalists who write about science to understand this. But it's also a problem for scientists and statisticians to be able to articulate what statistical significance really means in a way that helps people avoid these misinterpretations. Now, I ran across a very interesting, now that would be a different case. This is a year or so ago, there was a report that came out about an AIDS vaccine test that got widely mangled the way it was covered in the media because the statistical significance level was reported and interpreted in some of these bad ways. Not just by the journalists, but some of the scientists the journalists quoted made exactly this mistake of saying it was p.04, therefore it's a 96% sure thing that this thing works. And so it's very bad that the scientists who were quoted, and these were clinicians actually, who were saying, "Oh, great," But so this journalist from Science, who I will not name, you can see his name, to spare him embarrassment and alleviate the possible charges of slander against me. Talked to the chair of biostatistics at Harvard School of Public Health about this issue. And I thought this guy's pretty clear to the jurors. I mean, if there's a p-value of 0.4, it says probability 1 in 25, you've seen the results in this magnitude or larger if there were not true vaccine effects. So what is the journalist's response to that? I'm not making this up now. I'm taking this right out of this interview that was published by the journalist about his discussion. I think that means less 5% chance that I'm going to say this word related. And the statistician says, no, it's not like that. This is a quote I used last night. It's the difference between I own the house or the house owns me. This is, that's a great way of, summing it up. Or the way I re-summed it up. In other words, evidence that I don't own the house is not evidence that the house owns me. And that's kind of the best, really quick way of explaining the logical fallacy to people that I think I've come across. But anyway, so the journalist says, the editor is going to say, this sounds to me like it's, we got to put this in plain English. And if it's a 5% p-value cutoff, we have 95% confidence it's real. And the statistician says, no! How many times does he have to tell him? And it's like, I'm reading this and I'm thinking, what's journalism? That would be better. But it is, you see that language all the time, it is interpreted incorrectly. And the journalist says, it seems to me like it's just poetic license. Nobody who's working for me would say that. And it says, no, it's a huge qualitative difference. It's a whole different thing. And, and I guess my main point about this whole thing that I've been talking about is that if it were only the journalists who didn't understand it, it would be bad. Yeah, it'd still be terrible. But the problem is scientists don't understand it either. A large number of scientists don't understand it. And there are medical journals, all highly prestigious medical journals that publish papers that make statements that are very much just as dumb as this journalist's statements. And it's a huge problem. I do not understand why it can't be solved, but it's just, it goes on and on. And I have some examples. Here's, so what can you say what statistical significance means? I touch this. Well, it means maybe there's an effect and maybe there's not. You don't know. All you know is you saw something that maybe is unlikely to have been seen or less probable than you might have expected to be seen. It might be that that's because there was a real effect and the null hypothesis is wrong. Or it might be you just saw one of those things that's unusual to see. It's like I said last night. A few days ago, I was in Santa Monica. It rains less than 5% of the time in Santa Monica. It was raining on me, but that was not evidence that I was not actually in Santa Monica at the time. So, it's the real answer, of course, is you have to do some more experiments and see if you keep getting the same answer. And which is what good science, of course, is all about, reproducing the experiments, verifying, and all that. But there was a problem with that because in a lot of cases, in a lot of very important cases, like large clinical trials, the logistics and expense of doing those and repeating those is often prohibitive, and you have a case where you can't always do that. So you have to get into a little more understanding what's going on. Another important point that I have to make to journalists that I think is often missed in these discussions is lack of statistical significance does not mean that you've shown there is no effect. This is another serious flaw that shows up in the way some scientists reach their conclusions in their papers. They tested to see if this drug was dangerous, and they got the results, blah, 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 is not statistically significant, therefore this drug is safe. That's not a correct inference. All you can say is you have not found strong evidence that it's dangerous. It's not the same thing as saying it's evidence it's safe. It's that old absence of evidence isn't evidence of absence kind of thing. It gets misinterpreted a lot, misstated. So here, for example, is a study where a journalist would look at this report. This is an actual data from it's an old study that was some kind of nitrates for heart problem test or something. I don't remember the details, but it was a medical study of some intervention for heart patients. And here's a study that found it was supposed to help. Didn't look like it helped in this study. It looked like it was more harmful than helpful, but it was not statistically significant because that's a 95% confidence interval bar there. And you can see, if you can see the bottom, those are odds ratios down there, and the bar extends well into the possibility of helps and well into the possibility of harms. So the conclusion on this is not obvious. A lot of journalists would look at this and first say, oh, it looks like this harms. You know, it's a signal that it harms. This is like it caused more deaths in that group, but it wasn't at a statistically significant level. You know, no, it just, that was the numbers, and it was not statistically significant. You don't really have the right to make any judgments on this particular case. So there's two things here. Not only can you not conclude because there's a lack of statistical significance that this is not harmful or not helpful, you can't conclude that it's not harmful either. You don't know either way. And if they had been testing this to see if it harmed, if they thought this was something that was harmful, they tested it for that, got this result, they would say, looks like we might have been right. It does look harmful, but we didn't get good enough evidence to prove that. Whereas it might be translated, but it might be also, but that would be a correct thing to say. But what somebody might say, they tested to see if harm, the results were not statistically significant, therefore it's safe, which would not be the correct conclusion. So another test of the same thing got this result. Well, this is interesting because now you have another non-statistically significant result. But in this time, the group was looked like it came out a little bit better, but not by enough to say whether it was statistically significant or not. So how do you report that? Well, you would say, we don't know. Now, but over time, more studies were done. Fortunately, this was something that could be tested easily enough so that you could have a number of studies done. And ultimately, what you saw was that over the course of time, strong evidence was ultimately developed to indicate that this was a beneficial treatment. Especially if you see toward the bottom where you have the biggest study that was done, the size of the block indicates the size of the study, and the confidence intervals were much narrower, then you not only see that there's strong evidence that this is a helpful treatment, but you also see that the statistics actually worked pretty well in the long run because all the confidence intervals all overlap, so they're all consistent with each other, which is kind of a good sign, I guess, that maybe these are being well done. But in any case, it goes to show how taking any one of those studies alone and trying to draw a conclusion would not have been sound science. You had to have the validation by repetition of the study to come up with something that was reliable information. So this whole business of confidence intervals then is something I'm trying to do with my writers now, is get them to more and more report confidence intervals in when they write about a finding, not just report that it raised the risk 16% or 22%, but give the range of the confidence interval to give people a better sense of how precise and reliable that finding is. So, here are 3 points that, remember the original paper I put up made some of these points, and there's some issues about this to some extent, but because of the way statistical significance testing works and the way the publication system works, there are these 3 broad classes of things I like to point out, which basically have been identified in some of these other studies, that really raise the probability that the study that you're looking at is one of those wrong studies. One of those studies where you may have, where when you're trying to decide, is this really evidence of effect, or is it just one of the rare times you see something unusual? These are the kind of studies where it makes it more likely that you're seeing just the thing that's unusual and it's not a true effect, or that your conclusion is wrong. So the first report, there's some back and forth in the literature about this. There's some really good papers, I think, that establish first reports in a field are at least likely to overstate the true effect. And there's other analyses that indicate, at least in a lot of fields, in a lot of situations, the first report is the report that's most likely to be one of those statistical flukes, one of the outliers. It's understandable if you think about it, depending on the field, depending on what's going on. If you're trying to find a drug that works for something, and not very many drugs work, if you try enough of them, you're going to get some apparent statistically significant results for some of those that don't work just by chance. And if it's really hard to find the one that works, the one that you find first is likely to be one of those that arise by chance. So this tends to, at least in a lot of cases, make the first reports suspect. And many scientists know. That's why you say, if you get a first report on something, that these results need to be confirmed by further research. It is very often the case that a first report is wrong. Hot research field, that is another case where you have more chances for more flukes because more people are doing the studies. If you have 1,000 labs working on an issue, then if they're all geared up to publish as soon as they find something that hits p equals 0.05, you got 50 of them are going to be ready to go even if nobody actually found anything. And of course, in principle, it shouldn't matter if it's a hot research field or not, because 0.05 is 0.05, but you have publication bias in journals being more likely to publish the papers that get a statistically significant result than the ones that don't. It's harder to get it published if you don't get that finding. So in principle, the statistics would be not changed by it being hot if all the work that was being done was being promptly published. But the work that doesn't find them is certainly going to be delayed, and it's maybe never published, whereas the ones that find what looks like a result, zip into Science or Nature, and you're off and running. Contrary to previous belief is another thing that it should be a flag, because if a study comes out that is contradictory of previous belief that presumably was actually